This talk is about engineering modeling. Modeling is a technique that engineers use to simulate some aspect of system behavior. It's an essential tool in engineering design. It's used by all different branches of engineering, and it's always a part of the design process. Output from a model is used to make design choices. So models don't necessarily have to be a complete description of the system. They only have to be a view of the system that will help you make some design choice or another, set some parameter for the system that you're designing. Let me give you an example. Suppose we have a set of data. These are measurements that we've made as a function of time, and we collect 100 data points. Well, now we have the engineering task of trying to interpret the data, to understand the data. And you have in your toolkit already a very clear understanding of one kind of model that you might use to understand that data. And that model is a graph. For example, if you have a simple graph of your data, you can see that on the horizontal axis is time, on the vertical axis is the measurement, and if I plot each of those collected data points as a blue circle, then I get a much better feel than the tabular form of what actually is happening in this system. As time progresses, the measured sample is getting larger and larger. It doesn't appear to be linear. It appears to be some kind of nonlinear increase in the measured value as a function of time. So a simple graph is a great example of a kind of a model. A second kind of a model that we might employ for this particular set of data is maybe we would try to fit that data to some kind of mathematical model. For example, that particular set of data looks to me like it might be quadratic. So if I fit the best quadratic fit to that equation, to that set of data that I can, I might get something that looks like this. Here's a line. This red line passes through the data, and it's a line with a specific mathematical equation that the measurement is equal to t squared minus 4t plus 3,000. This happens to be a best fit line, meaning that if you took all of the possible quadratic equations that could fit that data, this one fits in a way that reduces the error of the fit better than any other one. So fitting of mathematical equations to data is one way to represent the data by a lower order model. Now, there's something that we need to think about when we think about models, which is the fidelity of the model. The fidelity describes how well the model fits with reality, particularly the reality that we're interested in modeling. Usually, higher fidelity requires somewhat more complex and expensive models. In other words, we've got to capture more of the physics than we would otherwise capture to get a higher order fidelity. Fidelity, though, is not the same thing as complexity. It's very important to keep in mind that a more complex model might not be a better representation of the actual system. Let me give you an example. Remember that data. So here's the data of measured values versus time. And we had decided in the last slide that we could fit that pretty well with a quadratic equation. Quadratic equation is a second order polynomial fit. But then you might ask yourself, hey, if a second order polynomial fits the data so well, why not go with a higher order polynomial? Maybe third order, maybe fourth order. Well, for the purposes of this class, I thought maybe let's try to represent it by a 16th order polynomial. So here it is. There's a 16th order polynomial, again, a best fit to the data. And you'll notice that the red line, that 16th order polynomial, does appear to come closer to those blue data points than the green second order polynomial fit did. Does that make the 16th order polynomial fit a better fit to the data? Well, it really depends on the physics, but I would say in general, looking at that data, no. I would say the second order fit is probably a better match to the physics of the system, and the 16th order fit is probably tracking noise, which is not useful to us. A big part of modeling is picking the right level of complexity for the model.